All right, so there is your equation for constructive interference, and you want to make sure that, of course, gets on cheat sheet. Now, similarly with destructive interference from the previous page, we had destructive interference with 0 lambda, lambda by 2, lambda, and you see the pattern from there. So the corresponding formula for destructive interference, so it matches with the one above. It was at 0 lambda was the y-intercept, or the first one, and then every one occurs lambda by 2 later. And again, we're going to go by according to maxima. So for the first one, for the first destructive interference, n would be 1. First, that term would go to 0, so it'd be 0 lambda. Cleaning that up, that one's a lot simpler to clean up. There we go. So there is our formula for destructive interference and constructive interference. And please, what you can do to simplify things for you, this is for reflected light. All right, because the next one we're going to is transmitted light. Okay, so please make sure that you know that these two formulas are for reflected light. Because now when you look at this particular page, you see that you have pretty much a similar page. So speeding the process up a little bit for you here, and I'll still go through the explanation, but you still have, we're looking at a thickness that's approximately equal to 0 lambda, so basically 0. And again, there's our thicknesses that we're referring to. This time, though, we're interested on the light on the opposite side. So the previous one was for reflected. This one is transmitted. All right. So same process, or exact same analysis. It's just we're looking on the opposite side here. So we have, in all three cases, the light waves striking. Now we're interested with the starting line being kind of on the opposite side, on the transmitted side. Okay, so what happens in there? Well, we get the refracted light, and then we get the transmitted light. Okay, some of that light might have been reflected, and then it gets reflected again at the next surface, and then transmits. So you have that possibility where you have that light travel twice. So let's talk about what's happening here. So for the green one, let's say it struck as a crest, it would enter as a crest, and because it's transmitted, it's going to start as a crest. Okay? Blue light, or the blue wave, starts up here as a crest, gets reflected, becomes a trough, becomes a crest, exits as a crest, and because the distance was 0, there's no phase shift there. So we end up with constructive interference. Crazy, eh? So we get constructive interference there. All right, similar patterns, it's just the thicknesses change. So here's our transmitted. So this one was a crest there, exits as a crest, so it's still a crest. And I'm arbitrarily, when I'm talking about it being entering as a crest or striking as a crest, it's just an easier reference for us. Blue wave, here we go, reflected, now it's a trough, reflected, now it's a crest, transmitted, should be a crest, but remember, it's traveled lambda by 4 one direction, so total distance here, so let's go, the extra length that's traveled is 2 times lambda over 4, or it's been shifted half a wavelength. Oops. Okay, so that's the shift. So I said it exited, so one more time. It starts as a crest, trough, crest, exits as a crest, but now I have a half of a shift. So that means that half a shift to get me to a trough. So actually the blue wave is out of phase. So we have destructive interference. All right. And the last one you've already probably predicted, it will be constructive interference. All right. So the green wave enters as a crest, refracts, transmits. It's going to be a crest. Our blue wave enters as a crest, reflected trough, reflected back to a crest, transmitted as a crest, but that shift we go through and look at the math on it. 2 times lambda over 2, because it's gone there and back, is now just lambda. So if it is a crest, one wavelength later is also a crest. So that's why we have constructive interference. All right. So what does that mean? On to the formulas. Well, I'm not going to go through. Just please make sure you mark this as transmission. Crossing these formulas up are very frustrating, especially in the homework and on tests, but it is the exact opposite of the reflection formulas. So please make sure you clearly mark them on that formula sheet for yourself, but they are backwards to our reflective ones. All right, so destructive interference. And again, the N is the maxima that you're looking at, the number of maxima. So this one again, lambda 2n minus 1 divided by 4. Okay, moving along. Talking about some of the formulas here. So equations for thin film interference. Just going to do some quick manipulations here. We know that velocity of light is equal to f lambda. Okay, so we've also talked about speed of light is designated as a c. So if we assume that the initial equation is the velocity of light in a different medium, all right, so if this is the speed of light in air equals f lambda, if we set it up as a ratio, so I want to divide it by the velocity in another medium, that means it would be the frequency in another medium. So I'm going to go lambda 1 and 2. Note that because it's being generated by the same source, then the frequency of light has to be the same. You can't change your frequency even if you enter into a new medium. So what that means for our relationship is that those frequencies actually drop out of the equation. So you're left with speed of light in air, speed of light in a new medium, wavelength in air, wavelength in a medium. Now recall, off to the side here, that N is equal to C divided by V. All right, so that is our new medium, N2, which means that our formula on the left gets simplified down to the index of refraction for my new material that it's entering into is equal to the lambda, the wavelength that's exiting, divided by wavelength of light that it's entering. So we find that relationship, which will also become very handy for us as we move through some of the examples. So into the examples finally. In the summer, the amount of solar energy entering a house needs to be minimized. So as soon as you see the word minimized, that means we're looking for destructive interference. Destructive interference is a good thing in this question. So we do this by applying a thin film coating to maximize the reflection of the light. So if the light has that wavelength, travels into an energy efficient window, what thickness of the added coating is needed to maximize reflected light? Maximize reflected light. So what do we know? Writing out my information or decoding this question, I'm looking for thickness. That's my unknown. I know that the lambda in air excuse me, is 568 nanometers. And I know that the coating that we're entering, N2, is going to be 1.4. All right. So what do I know? I know enough that I need to find the lambda inside the film, okay? Because the light is going to enter our film. All right. So I need to find the wavelength. Need to find the wavelength in that new film. So from the previous formula, I have the medium we're entering. The index of refraction is 1.4. The lambda of light, the wavelength of light in air, is 568. And actually, let's convert that to SI so that we don't run into problems a little bit later on here. 5.86 times 10 to the negative 7th. And we're looking for that new lambda. So doing the calculations here, 4.2 times 10 to the negative 7th meters So therefore, in the film, lambda of light is 4.2 times 10 to the negative 7 meters. So I want to cause maximum reflection or maximum destructive interference. So we go back to our formula pages. So if I want to, oops, too far, maximize, I'll go back a little further here. If I want to maximize my reflected light, all right, I know that it's going to be lambda over 4. So I'm trying to maximize my reflected light. Or if I'm trying to maximize my destructive interference, my destruction of that light, it's going to be the same formula, lambda over 4, because when we put n equals 1 in, you end up with lambda 2 times 1 minus 1 over 4. So that becomes just lambda over 4, just to show you. So actually, you can't pick wrong here as long as you're consistent with your thinking. So, continuing up here, therefore, our thickness has to be lambda over 4, which means that 4.2 times 10 to the negative 7, we're going to divide it by 4, and we're going to end up with 1 times 10 to the negative 7 meters. So therefore, the film must be 1 times 10 to the negative 7 meters thick. So fairly thin film. Now that's the calculated one. In reality, if you were coming in, probably impossible to apply it that thin. So what you would do is you would ramp it up so many thicknesses in order to get it to a point where you can actually apply it successfully. So that means your N value, instead of using 1, you may be using 10, 15, 20, depending on the product, but you're increasing the thicknesses until you get to that layer level where you can actually apply that thickness appropriately. So there you go. There is the assigned homework that deals with this particular topic. Be helping you in class tomorrow. If you have any questions, please let me know. And if you want anything clarified, you want me to go through and kind of make it a little bit more understandable or step through it, I'll also be glad to do that for you too. All right, we'll see you tomorrow.